Let's look at number 14 from task number 9. Using limit notation, describe the end behavior of the function. So we're doing this without a graphing calculator. Notice that we already have a numerator and a denominator that is written in standard form. So the highest exponent all the way down to the lowest for both. So the first thing we're going to do is we're going to analyze the exponents. And we can see that the degree of the numerator, it's 3. It's not less than the degree of the denominator. If that was the case, we'd have a horizontal asymptote at y equals 0, also the x-axis. If the numerator and the denominator had the exact same degree, like 3 and 3, or 2 and 2, then we'd be able to identify the horizontal asymptote by taking the leading coefficients, in this case, if that was true, 5 and 1, and we'd divide the leading coefficient of the numerator divided by the leading coefficient of the denominator in order to identify the horizontal asymptote. Now, this is the case for number 14. The degree in the numerator is greater than the degree in the denominator, and when that occurs, there is no horizontal asymptote. And in fact, what happens, we have a slant asymptote. Now, how do we determine this? Is we're going to do polynomial long division. So we're going to take what's in the numerator always, and that's going to go inside, making sure that all things are accounted for. So notice that we have degree 3. I need 3 all the way down to 0 accounted for. So there's 3, 2, 1, and 0. So everything is accounted for. And on the outside, everything also needs to be accounted for. There's 2, 1, and x to the 0. And is it necessary to put x to the 0? No, but there does need to be a value that's in that position for the placeholder. Now, as a quick reminder, I know that many of you have not done this since first semester. How do we go about doing this? We're going to ask ourselves, x squared times what value equals 5x to the third? So I know there's a hidden 1 here. So 1 times 5 is 5. I need a total of 3 x's, but I only have 2. So 1x squared times 5x would be 5x cubed. This is what I came up with. So I find the right column. Here's just the x's. I find the right column, and in this case, I'm going to write 5x. Now I'm going to multiply. 5 times a hidden 1 is 5, and a total of 3 x's. 5 times negative 3 is negative 15, and 2x is 5 times positive 2 is positive 10, and 1x. Then everything on the second line always is going to change the sign. It's like we're multiplying by a negative 1. So it was positive, make it negative, negative becomes positive, and positive becomes negative. And then we combine these. These, if you did it correctly, the very front ones should always eliminate themselves. They should be exactly opposite. Here we get 16x squared and negative 40x. Okay, we're ready to start again after we bring down the next number. So I'm underlining and underlining. I'm asking myself the exact same thing. 1x squared times what quantity is 16x squared? And the answer is 16. Okay, multiply 16x squared, multiply negative 48x, and multiply a positive 32. And we change the sign of everything on the second row. It was positive, make it negative, make it positive, make it negative. Now combining they cancel, and 8x, and this is going to be a negative 31. Now that's my remainder. When we figure out the equation of the slant asymptote, we don't care about the remainders, we care about what's just up on top. So this is the equation, this is the equation. And so we're going to talk about how do we write that in limit notation in just a second, because that's what we were asked to do. But first, let's take a picture idea of what this looks like in terms of it being a picture. Let me find this. Okay, so I've gone ahead and I've graphed this. This is the function we were given. And then I inserted the equation of the slant asymptote. And you can see as it goes to the far left, it's getting closer and closer. It almost looks like they're on top of each other. It's not the case. If I zoom in, you can see it's getting closer and closer as it moves to the left to that slant asymptote. And as we move to the right, it's getting closer and closer to the slant asymptote, which is blue, but it never actually will intersect it as it goes to the far left and to the far right. Next up, how do we put this in limit notation, which is different. It's not something that we covered in the curriculum, but definitely something that you can understand. Here we go. So we're going to talk about this limit as we go to the far left and also as we go to the far right. So that's how we describe it, the far left, and we're talking about this function. This function was, if we look back up here, this function was r of x, okay? So the function r of x as we go to the far left is getting closer and closer to what? To the slant asymptote. And the function as we go to the far right for r of x is also getting closer and closer to the slant asymptote. So this is how we write the slant asymptote as we go to the far left in limit notation our function is getting closer and closer to the slant asymptote, and in limit notation, as I go to the far right, our function is getting closer and closer. Will it always be like that? This is how we're going to write that. That is correct. So once you find this, you would place it in both of these positions. And you do need to account for as it goes to the left and as it goes to the right.